Okay, thank you very much. Hello, everybody. So my intention is actually to keep this talk really lightweight. I'm not going to throw a lot of sort of new radical research at you or anything. I just want to expose you a little bit to the field of graph analytics. So increasingly important, really exciting, and show that there's actually a lot of low-hanging fruit as well as far-ranging research opportunities here. Okay, so that's it. Kind of sit back, enjoy. This is going to be pretty lightweight. Okay, so and I should mention that this work was done with one of my PhD students, Priyank, and a couple of collaborators at Oracle. Yeah. Okay, so first of all, why graphs, right? So graphs are just a really natural way to represent relationships between certain real-world entities, okay? So basically in a graph representation, each object is a vertex, right? And relationships are represented as edges between these vertices, between these objects, okay? So canonical example, of course, is something like Twitter, where we have various users, right? And the canonical relationship in Twitter is the follower, somebody follows somebody else, right? And so we have sort of different users, for example, following the ARM Twitter account, okay? Now, it turns out that in the real world, a lot of graphs have a particular property which is basically a power law distribution in popularity of the vertices, that is, in the connectivity between vertices, okay? So graphs that have this property are often referred to as scale-free graphs, or a much easier thing to say is natural graphs, right? And that tells you that this is actually a pretty fundamental type of a graph, okay? So the property is quite simple. It's that a small fraction of the vertices have really high connectivity, and then the vast majority have significantly lower connectivity, okay? So there are all sorts of networks that sort of exhibit this property. So for example, connection networks, let's say the internet, right? There are a couple of nodes that have massive connectivity, not a couple, relatively few. Financial networks, again, banks have very rich connectivity, whereas individual accounts within the bank obviously have very low connectivity to other accounts, right? Social networks, again, being the canonical example, right? If we take Twitter, for example, these are real numbers. An average number of followers for a typical user is 700, okay? But if you look at some of the extremes, like the gentleman in the picture, it may be in excess of 90 million, right? But obviously there are very few Barack Obamas in the world, right? And so this is massively skewed by these sort of several, users, small fraction of the users. Okay, so that's graphs. Now, graph analytics is simply an algorithmic way of extracting meaningful, interesting information out of these many-to-many relationships captured in the graph, okay? There are lots of applications of graph analytics. For example, I have a list here, so community analysis. That might tell you something, for example, about the existence of communities or sub-communities that are not readily visible within a larger graph. So one really interesting application of community analysis is, for example, for counterterrorism efforts, right? So you have some sort of a graph, right? Again, be it on a social network, be it in a financial sense, right? And you want to find little hidden sub-communities that may tell you something. Similar thing is done, for example, in recommendation systems, right? So if I've watched a bunch of movies and there are a bunch of other people whom I may never know and meet who have watched similar movies, we form sort of a community, right? And so this is a great foundation for making movie recommendations, right? There have been some really amusing sort of anecdotes about using sort of this type of analysis to infer some really strange things. So for those of you who know this meme, this is the, apparently men who buy diapers are statistically very likely to buy beer as well, like on a single, sort of like diapers in one hand, six-pack in the other, right? You can go read about this, by the way. This is like highly debated whether this is real or not. Like this was apparently revealed by Walmart, like, 2 decades ago. Anyways. Okay, now, getting into slightly researchy things here, the problem, of course, is that in the modern world, right, today graphs are often very large, right? Very large, meaning, maybe gigabytes, tens of gigabytes, occasionally, for some very, very large problems, hundreds of gigabytes, right? This is significantly larger than the caches we have, or most likely will ever have, on-chip caches, right? And so as a result, what we end up with, because of these fairly irregular access patterns, and this goes back to the first talk in the session about prefetching, we end up with frequent misses in our on-chip caches, most importantly in the last level cache. Because remember, if we miss in the last level cache, we're going to memory. This is hundreds of cycles. The CPU is exposed. Things are not good, okay? So because of frequent LLC misses, applications are often memory bound. What makes these things particularly difficult is that normally when we run a graph analytic workload, there's actually very little compute that happens for every vertex processed. Very little. I mean, it's pretty much load the vertex, do some trivial arithmetic here and there, and then move on to the next vertex. And again, this is pretty much what Timothy was talking about in the first talk. So the bottom line is that because of these frequent LLC misses, we end up with very poor performance as measured by normal performance metrics like instructions per cycle, or the inverse of that, cycles per instruction. On graph analytic workloads on non-trivial, like kind of real-world data sets. And we look at a CPI stack, basically the breakdown of time, where does the time goes in the processing of these workloads. Okay, what we see is that accesses to main memory basically dominate the execution time of these workloads. Okay, so this is a very simplistic picture, but this is real data collected in real hardware. So on average, what we see is that DRAM stalls account for 40 to 65% of total execution time. We're just sitting there waiting on memory. That has a very interesting implication that I'll get to in the back end of the talk. Okay, so what we really want to do is to improve the cache efficiency of our graph analytic workloads. Now, I want to say that I really like Timothy's talk earlier about prefetching. I'll mention something along those lines at the end of the talk. So I think that's one way to improve performance. Another way to improve performance is actually to directly attack the problem and actually make sure that the stuff you need sits in the cache in the first place. Okay, and that's a little bit of what I'll get to later on. But again, let's talk a bit more about the background material, just so that again you guys understand how these applications are structured and where the opportunities arise. Okay. So the canonical processing model for graph applications, not the only one, this can get very religious. This is not my objective here, right? But the canonical processing model is what is known as vertex-centric processing, okay? And the idea is there's a canonical operation that happens for every single vertex in the graph, and so the perspective is with respect to the vertex, right? So for every vertex, we do a particular set of operations, and then move on in some algorithmic fashion to the next vertex and repeat, okay? So normally it's for a vertex, traverse all of its edges. For each edge, access the property of the vertex on the other end, compute something, and then move on, right? As I said, this is not the only processing model. There are some advantages, especially for certain types of algorithms, to doing edge-centric processing, asynchronous processing, lots of sophistication. This is pretty damn good for most people. Okay, so just sort of a cartoon example of what I just said, right? Given vertex 1, what we would do is traverse all of the edges, to vertex 0, vertex 2, vertex 5, right? And then based on that, maybe we'll compute the property for vertex 1, or maybe it's the opposite. Maybe we'll propagate some property of vertex 1 to those neighboring edges, okay? Now, before I move on, I just want to point something out in this graph that is really interesting and that is relevant and that I want to draw your attention to, which is important later on in the talk, which is notice that vertex 1 is our typical sort of not well-connected vertex in the sense that there's only one incoming connection to vertex 1, and that is from vertex 2. Okay, so there's only one incoming connection. So this vertex is not richly connected to others. However, vertex 1, and so like, if this is Twitter, this guy is a nobody, right? This person is a nobody, and so it just follows a bunch of sort of famous people. But if you look at vertex 5 in the lower right-hand corner, we see that, this is your Barack Obama, right? There is lots of connections going into vertex 5, right? And absolutely, no outbound connections, right? Because I suppose Barack Obama doesn't have a lot of time for Twitter, unlike, other popular figures. So, okay, so, right. Okay, so that is sort of the processing model. Now, the data structure is really, really important. The most common data structure, again, not the only one, right? There's no religion here. But the most common data structure in use today, for very good efficiency reasons, is something called a compressed row storage format, or CRS format, okay? And basically, all it is it's a very space-efficient representation of graphs that is based on at least 3 arrays. In the rest of the talk, I'll only focus on 3 arrays. There are some algorithms that require at least 1 additional array, but again, it all looks very similar in the end, right? And the 3 arrays are the vertex array, so this is the set of vertices we have, right? Those are the ones that are shown in the figure with circles. The edge array, so for each vertex, it's a set of edges. Depending on the algorithm, like depending on the thing we need, these could be outbound edges or inbound edges, okay? So it's algorithmic specific, but it's a set of edges, right? And then the compute array, which is basically the state of each particular vertex, okay? And so basically the vertex and edge arrays encode the graph structure, and the compute array is the value that we're interested in, okay? So for example, if we're computing the page rank, the compute array would actually hold the page rank of each individual vertex, right? And so the way the processing works is, we access a vertex index in the vertex array, right? And then, we access the set of edges through the edge array. So again, notice that vertex 1, the highlighted vertex, has 3 outbound edges, right? And so for each edge, what we would do, again, this is page rank. So we're propagating the rank of this particular vertex to our downstream neighbors, right? And so this is what we'll do, is for each edge, we'll push the rank downstream. Okay, so 3 edges, and we do these 3 downstream pushes. Okay. Okay, and now let's kind of come back to this question of what does this mean for cache efficiency? Okay. If we look at the access patterns of vertex and edge arrays, they're actually ridiculously regular, right? Ridiculously regular. Again, this is page rank algorithm. They're not all exactly the same, but they're all pretty damn similar, right? So, we're basically going to stream through the vertex array. For each vertex, we're going to stream through the edge array, right? And so the bottom line is these are highly regular accesses, right? So it's a sequential access pattern, amazing spatial locality, perfect for L1 caching, really well exploited, really easy to prefetch with any sort of dumb prefetching, right? Again, I'm not saying there are no issues of timeliness and whatever, right? But this is obvious. This is not difficult, okay? And also, there's really no reuse for at the last level cache, because even if we're doing multiple iterations, multiple traversals, concurrent, sequential, whatever, right? By the time we come back to the very first vertex, by the time we come back to the beginning for a reasonably sized data set, this is like we've touched billions, potentially, millions of vertices, billions of edges, right? So this stuff, it's very questionable how much benefit there is to cache this. Now, when we look at the compute array, we notice a completely opposite phenomenon, right? So what we see is that while we're accessing the vertex and edge arrays in a very regular fashion, the compute array is basically accessed in a highly irregular, essentially random fashion, okay? And so the implication of this is that the locality in the compute array is extremely poor, so there's virtually no spatial locality, right? And the temporal locality in theory exists because vertices that are highly connected will see, right? So in the earlier example, right? Let me just go back. Vertex 5, right? Highly connected vertex, lots of incoming edges, right? You will see reuse, but that can happen at pretty large temporal localities. Not easily captured. Okay, and so basically compute array accesses dominate both LLC accesses and misses, okay? And so this is what this graph shows. This is accesses to the last level cache within the compute array So I apologize. The legend says compute list. It's compute array, same thing. And then accesses to any other data structure, anything else outside of the compute array. And what we see is that the vast majority of LLC accesses on a real machine, these different applications, right? It's all dominated by accesses to the compute array, right? L1 cache is fantastic locality. And then when we look at misses, and again, misses are normalized to accesses, so you can see that 70 to 80% of all LLC accesses miss. The vast majority of misses are again coming from the compute array. So if you really want to attack the efficiency problem of graph analytics, you really only have to focus on one array, one data structure. Everything else is very, very easy. Okay. Okay. So how do you improve the efficiency of graph analytics? I mean, basically, let's focus on the the thing that's giving us the most trouble, which is the compute array. Okay, and the way we're going to do this is by exploiting the fundamental property of these data sets, which is skew, right? We have some vertices that are highly connected, and there are not a lot of them, okay? And so that's a small fraction of the vertices, highly connected, and the rest of the vertices have very little, and in many cases, literally no connectivity. They're completely useless, okay? And so what we want to do is we want to cache highly connected vertices. Now, remember, we have caches. They're already trying to cache things. They're massively inefficient. Why are they inefficient? Well, because the access pattern is what the connectivity is what determines whether something is highly reused or not, but the access pattern is pretty random, as we saw earlier, right? And when we look at an individual cache line, right, any random cache line, right, what we see is that at most, a random cache line will have one highly connected vertex surrounded by a bunch of vertices with low connectivity. Okay, and so the solution is really, really obvious. Why don't we just pack highly connected vertices? Okay, pack them into a cache line. So that way we actually have cache lines that are highly valuable. Every single vertex is highly connected. That way we're likely to maximize both we're certainly maximizing spatial locality, and we can also improve temporal reuse, because guess what? A hit to one of these vertices will guarantee, will basically promote the cache line, which improves the chances of another vertex or the same vertex hitting in the near future. Okay. Now, a naive solution is to sort the vertices by connectivity. Okay, and so we'll literally reorganize the entire array in a way where we go from the most highly connected vertex to the lowest connected vertex. Okay, that's a really, really intuitive way to do things, right? Turns out that's not so great for two reasons. Number one, there's a high algorithmic cost to this, right? We're going to touch every single vertex and we're going to sort them. The second reason is a little trickier, and it's a lot more insidious runtime-wise. So a lot of graphs have underlying structure. Okay, and so the structure actually determines the access pattern, right? So communities, for example, okay? And so complete sort will totally decimate the structure, okay? And we'll see this, the effect of this later on when I show you a couple of simple results, okay? So a much better way to do this is to just very coarsely group vertices based on connectivity into, roughly speaking, two buckets. Highly connected bucket and everything else. And within those buckets, we're going to preserve the order, okay? So here's an example of this. We're going to toss things into buckets. So this is a, vertex with low connectivity, vertex with high connectivity, and we're going to keep tossing things into buckets. But notice that I'm not making any effort to sort things within each bucket, okay? I'm simply separating these two things in each group while preserving the original order of the vertices within each group, okay? And so algorithmic complexity is linear, super cheap, and at least superficially it looks like I'm preserving structure. Okay, I'll quickly show you some results. So we're looking at the largest publicly available data sets, at least the ones that we know of. So most of these, except for one, have over 1 billion edges. So these are pretty damn large. 4 different graph applications, off-the-shelf framework, which I forgot to mention here. This is Galois. Running on a real machine. And basically, wow, nice. Let me see. Let's try this again. This could be the most interesting set of results you guys have ever seen. Damn. Huh. Interesting. What happens if I maybe just copy the slide? Let's see if that helps. Crap, it like flashes and then, okay, there it is. There it is. Okay, so sorry, this was animated. For some reason, animation doesn't work. But what I wanted to, what I wanted to show is that in gray is sorting. Okay, so that's like a full sort. And in dark is this. I know I'm almost out of time. I'm wrapping up. In dark is this grouping thing that I suggested. And as you can see, going below 0, this is a slowdown. Sorting is often very detrimental to performance. Except for one case, grouping is never detrimental. On average, grouping gets us about a 20% speed up. This is purely software, linear algorithmic cost. I mean, this is nothing in the grand scheme of things. We're getting 20% speed up on a real machine at virtually, for free. There are a couple of cases where sorting outperforms grouping. These are on the smallest data sets. Okay, yeah, and that's pretty much it. I'm out of time. We've also looked at hardware support for further improving things, and it turns out that with like ridiculously simple, trivial hardware, I'm not going to bore you with details. You would cry if you saw how simple and boring this is, right? We can like further double our performance gains. And okay, so Timothy already talked about software prefetching. That's I think that's really cool, but he kind of stole my thunder there. Plus, I don't have data anyways. And then I think the really cool opportunity is looking at future memory hierarchies in terms of graph processing. I think I'm going to stop on the slide. If you're interested in this stuff, please talk to me. I have a lot of thoughts on this, but again, not part of this talk. So that's it.